Section 7.2 is on right triangle trigonometry. So we've got some interesting ratios that show up quite often, and so we give them specific names. So we start with the idea of basic trigonometric ratios. We start with the idea of a triangle given by sides little a, little b, little c, and then we'll have angles capital A, capital B, and then we could have capital C, but it's always going to be 90 degrees. So for a right triangle, our capital C, we can always think of it as being 90 degrees. So we define the sine ratio is defined as the ratio of the opposite side, the side opposite the given angle, a given angle divided by the side divided by the hypotenuse. So we should actually, before we go into that, we want to be careful that we think of given angle capital A, we think of the opposite leg. The leg opposite angle A is little a, adjacent is going to be little b, and then for the angle capital B, the opposite angle is little b, the adjacent angle is going to be little a. So opposite basically means not connected to the angle, adjacent means that it is connected, it forms one of the legs that forms the angle. So the sine ratio is defined as the ratio of the side opposite a given angle divided by the hypotenuse, and so we notice we can say sine, we'll often abbreviate it without the e, we'll say sine of angle A would be lowercase a divided by lowercase c, the sine of capital B would be lowercase b divided by lowercase c. So opposite over hypotenuse. So, for example, if we said that we had a triangle and we knew that we had angle A, angle B, and we knew the side lengths were 3, 7, 6, we notice that the sine of A would be 3/7, the opposite side is 3, the hypotenuse is 7, and the sine of B is going to be 6/7. So, nice and neat. Don't have to think about it too hard. We'll also have, so we notice we'll never take sine of C. We'll talk about what that would mean later, but we notice that for the moment we're just interested in the idea of opposite over adjacent, opposite divided by hypotenuse. The cosine ratio . for a given angle. So a given acute angle in a right triangle is defined as the ratio of the adjacent side, whoops, one letter too many, and the hypotenuse. So it's very similar to the sine ratio. And if you took a full-on course in trigonometry, you'd notice a lot of very interesting similarities between sine and cosine. And so we notice that, again, we'll abbreviate cosine as just cosine of A will end up being the adjacent side divided by the hypotenuse. Cosine of B will be the adjacent side divided by the hypotenuse. And so we notice that if we looked at 12, 5, 9, and we had angle A, angle B, we notice that cosine of A is equal to 9/12, and we notice that if we can, it doesn't hurt to simplify. That's not a focus of this class. And cosine of B will be, the adjacent side is 5 divided by 12, and so we get those two cosine ratios. So we actually notice that in both of these cases we can actually make use of, if we know all three sides, it's actually interesting that if we know all three sides, we're going to learn about a couple of theorems later on, probably in section 7.3. Knowing all three sides dictates what those two angles have to be. So you actually notice that, especially for a right triangle, this is convenient. So you'll notice your calculator has a key. Oftentimes you can do inverse cosine. So that'll sometimes be second cosine. Or you could have a key that says cosine inverse. And you notice that if you tried telling your calculator cosine inverse of 5/12, this will give you some angle. We know what angle that has to be. It won't be a nice angle, it won't be any kind of integer, but we could do it. So in actual practice, what we'll notice is that if we were told something like the angle is 30 degrees, and we knew that, what do you want to say? If we know that the angle is 30 degrees and we knew that one of the side lengths was 6, it turns out we can use sine and cosine to figure out the rest of the triangle. We notice that the sine of 30, again we can use our calculator, sine of 30 will tell us that it's equal to 1/2, but we also know that if we call this side B and side C, we know that sine of 30 is 1/2. We know cosine of 30. Actually, we'll skip that for the moment. We don't need that just yet. If we say sine of 30 is 1/2, actually, let's use cosine. That'll be better. Oops. Actually, we use cosine of 60. So if we say cosine of 60 degrees equals 1/2, we notice that we can say cosine of 60 also has to equal 6 divided by c, and so we notice that 6 divided by c has to equal 1/2, and we can solve for c. We can find out the 12 equals c, and so we could also figure out b if we wanted to. We notice that 6 squared plus b squared has to be 12 squared, so we know 36 plus b squared has to be 12 squared, 144. And so we find out that we can subtract 36. So b squared is 108. And so we find out that b is the square root of 108. And if we felt like it, we could find out that 108 is 2 times 54, which is 4 times 27, which is going to be 36 times 3. Square root of 36 times square root of 3, and so it turns out to be 6 radical 3. But that's not something we have to know about. It's nice to simplify if we can, but not a focus of this class. So if we looked at, say, a 45-degree angle, and we knew that the hypotenuse was 12, just because we'll stick with 12 for the moment, we noticed we could figure out sides A and B, because we notice that it's a right triangle. We know sine of 45. If we put it into our calculator, it turns out to be, well, we'll find out possibly that it's going to be exactly square root of 2 divided by 2, which is going to be around, that would be approximately 0.7 something. And so we notice that we could say sine of 45 is also equal to b divided by 12. And so we can say that's b divided by 12 has to be approximately 0.7. And so we can say b, we can multiply both sides by 12. b is approximately 0.7 times 12. And so we end up getting approximately 8.4. And then we'll notice that A will also be approximately 8.4, because that's also a 45-degree angle. Also 45. And then our last standard trig ratio is tangent. The tangent ratio for an acute angle or a triangle is defined as the ratio of the opposite side and the adjacent side. And so we'll notice that we'll abbreviate that as tangent of our angle is equal to opposite divided by adjacent. So for our example triangles, we get A divided by B. And tangent B would be still opposite over adjacent, but now we get B divided by A. And so if we looked at a arbitrary triangle, 7, 3, A, B, we notice the tangent of A would be 3/7, tangent of B would be 7/3. And so you notice tangents and sines of the acute angles are very closely related to each other. And then if we know what the actual angles were, we notice that we could, again, we notice that we could figure out side C if we wanted to. We notice that C we could get either by saying C squared equals 7 squared plus 3 squared. So C squared equals 49 plus 9. And so C squared equals 58. C would be the square root of 58. But we also notice we could say that angle A, for instance, is the inverse tangent of 3/7. We can again use that inverse angle idea. Again, your calculator, it'll often be second tangent or something like that will give you inverse tangent. And we could find out that angle, and then we notice that we could say sine of A has to be 7 divided by C. So it turns out we know that sine of tan inverse of 3/7 the sine of inverse tangent of 3/7 should equal 7 divided by C. So we can go back to our calculator. We can find out that the inverse tangent of, let's get the correct number, 3 divided by 7 is going to equal approximately 0.428. And so we can take inverse tangent, so let's call it 4.286. So we're saying sine of inverse tangent of 0.4286 equals 7 divided by C. So if we take inverse tangent, we'll get where'd that go? Let's make sure we're doing this correctly. Oh, that'll work. That's better. So we're going to get 23.2 degrees. So that'll be sine of 23.2 degrees equals 7 divided by C. And so we can find out that the sine of 23.2 is equal to 0.3939. So we know this is actually going to be approximately 7 divided by C, approximately 7 divided by C. And so we find out that C is approximately 7 divided by 0.3939. So we can check that. We get 7 divided by 0.3939 gives us 17.8, so approximately 17.8. And we notice that if we take the square root of 58, that is a lot bigger, so we did something wrong. So let's find out what. So the square root of 58 is 7.6. So that's more reasonable. So what did we do wrong? So we have 0.4286 is correct. And if we take inverse tangent, we get 23 degrees. Oh, that's the trouble. You notice I said sine, but we notice that with that 3/7, we notice that we said 7 divided by c. Yep, that I should have used sine of a. We should have said 3 divided by c. So you always have to watch out for that. You have to make sure you use the correct ratio for the correct task. So we're saying sine A is 3 divided by c, 3 divided by c, 3 divided by c, 3 divided by c. And now we take 3 divided by 3, if we take 3 divided by 0.3939, we get 7.6. And so it matches our Pythagorean theorem. And so what you'll find is that this is useful because we notice we won't always have all three sides. Quite often we might be given, say, a side of an angle of 60 degrees, a side of 16, and we notice that we could actually use that to get both of the other sides, because we notice that we could say tangent. Actually, we'll use the trig function. We know we'll call this A and C. We know the cosine of 60 degrees is 1/2. So if you took your calculator and told it cosine of 60 degrees, notice that you have to be careful. You'll have a button on your calculator that says deg, or you'll see deg, oops, grad. We actually have three ways of thinking about angle measures. Deg is degrees, which is what we'll be using most often. You'll also see rad is for radians, which is a different measurement system for angles that you would use more in a physics class. It tends to be more technical. Degrees is a more common measure for angles when we're just thinking of it conversationally. So you make sure your calculator is set to degrees. So we notice that cosine of 60 degrees is 1/2, but we also notice from our knowledge of the ratio, we know that cosine of 60 should also be equal to 16 divided by c, the adjacent divided by the hypotenuse. And so we know 16 divided by c equals 1/2. And so we know 32 equals c. And now we can find out a. We can find out a either from trig. We could say tangent of 60 is equal to a divided by 16. But that's a little bit messier because tangent of 60 is not quite as convenient. That would actually wind up being we would actually have to take, we get radical 3 divided by 3 equals a divided by 16, and so it would turn out that a would equal 16 radical 3 divided by 3. Does that work right? We notice that if we checked, if we compared it to Pythagorean theorem, we notice we'd find out that 16 squared plus a squared would have to equal 32 squared, and so we would get 256 plus a squared would equal 1024. So a squared would equal, it's actually kind of convenient, we wind up getting 768, which turns out to be, a squared is going to be 3 times 256, and so we wind up getting a is going to be the square root of 3, square root of 256, and so we get 16 radical 3. So we did something a little wrong. What did we do? Oh, that's why, because tangent of 60 is actually just be radical 3. I always have to be careful about that. Again, that's not something you're going to really desperately need to know. You'll mostly really get that from your calculator. We also notice that we have something you may have heard of is the idea of SOHCAHTOA. Again, not something you necessarily need to know, but it's convenient. Basically, it just is a mnemonic to let us know sine equals opposite divided by hypotenuse, cos, use the abbreviations, cosine equals adjacent divided by hypotenuse, and tangent equals opposite over adjacent. And so it's just a convenient acronym that helps to keep those organized.